So we can start this lecture about chapter 9 of gas dynamics, oblique shock and expansion waves. First of all, first part of this chapter, we are talking about shock waves, and I will give you also some examples about calculations of the shock waves which have relation to work 1, which has to be delivered by the middle of next month. And after we will study expansion waves that have no direct relation to work 1, but as an important application that helps us to design many aerodynamic structures, for example, like nozzles, make profiling of the nozzles, calculate expansion waves. So we will be able to know this question as well. Last time we studied normal shock waves, theory of normal shock waves. I showed you how to calculate transition of the flow from supersonic to subsonic through shock wave, which is perpendicular to the flow. And oblique shock wave theory is based on a similar concept. It deals with a shock wave which is not perpendicular, but it uses part of normal shock wave theory because process has similarity, just inclined with respect to normal position of shock wave. So oblique shock waves happen in supersonic flow, same as normal shock waves. They appear when flow conditions and the geometry of the body are compatible with the oblique shock waves. Otherwise, will be or no shock waves in case of isentropic structures or subsonic flow, or could be bow shock waves or normal shock waves, which we already studied in our previous classes. Let's talk about these two structures. We will compare shock waves and expansion waves. They are in the same chapter that Anderson shows us, but these two processes are not similar at all. Flow which goes through oblique shock wave is case A, which you can see on this picture, is decelerating the flow. Flow loses part of velocity, it loses part of its total energy. This flow is not isentropic. Same time, there is an increase of, sorry, my video looks like it's not working anymore. Same time, there is an increase of thermodynamic properties and drop of Mach number. Inside expansion fan, we have a process that is different because it's a continuous change. Continuous change of flow properties and flow directions. Such flow is isentropic, and it increases Mach number and reduces other thermodynamic properties. When happen oblique shock wave and expansion fan, it depends on the flow properties before. It must be supersonic, but also must be an angle which is compatible or with oblique shock wave or with expansion fan. Its angle is shown here as theta. I see that also my screen is not so fast updating. So if you have some problems to understand what I'm explaining, please write your question in comments, and I will see, and I will try to reflect on your questions. We have for convex flow or for expansion fan, we have this data also, but now it goes to negative direction. So theta must be expanding the flow. So expansion fan must increase the flow area, the total flow area, which we can see here. In the case of oblique shock wave, flow is compressed. Okay, so the area of the flow reduces. So reduction of the area, oblique shock wave, increase or rise of area is expansion fan. Not non-isentropic process in oblique shock wave, and is isentropic process in expansion fan. So entropy is constant. And in the case of oblique shock wave, entropy is not constant. So this is the difference. Actually, you will see that models of these two processes are completely different. They are based on very different approaches. But since they have some kind of similarity, that flow rotates in a duct, so it changes its direction, they are in the same chapter of the book. Again, Anderson reminds the reason or mechanism why and how shock waves appear in flow. Flow must be supersonic, so disturbances from the body go in all directions. Usually, the total disturbance velocity is a sum of flow velocity and disturbance velocity, which is distributed always with the speed of sound in a medium. Okay, we know that speed of sound is different at each point, so it's field of flow property. We can remember that speed of sound is calculated as gamma RT, where temperature always depends on coordinate. At each coordinate, we have different temperatures, so we have different speed of sound at each point, not just on single flow line, but at any discrete point, we have different temperature and different speed of sound. So it's not such a linear process as we might imagine. In case of figure 9.3b, we know that on the body, probably here in the middle of the body, we will have stagnation properties, stagnation temperature, which is maximum temperature in the system that we could reach, right? So here at this point, speed of sound will have its maximum value, and when we are going far from this body, we will have some other temperature which is significantly different from the temperature on the body, and the propagation of sound waves in this region is different. So I think it's more or less clear. How much different we always can know by looking to, for example, Appendix A, which tells us function of temperature change as dependence on Mach number of the flow. I would like to remind you that there is always a function T0 by T or T by T0 in different parts, in different chapters is different, right? Is a function of Mach number always. So since we assume that in all region of the flow behind the shock wave, flow is isentropic, so this function, this analytical function, works and describes perfectly change of temperature with respect to change of Mach number. So we can know temperature change. And if we consult in Appendix A, just a moment, I will open here and I will tell you how different is this temperature. Okay. We will see two different values. That one Mach number is on the point behind the shock wave, the maximum possible velocity after the shock wave can be seen from Appendix B from the book. So just a moment. For the weakest shock wave, it's Mach number close to 1. Okay, this Mach number maximum possible in case of bow shock wave is close to 1 or approximately 1. And the stagnation temperature Mach number is always 0, a stagnation point. And if we open Appendix A and look for Mach 1, okay, just a moment. We'll try to copy this part of table on the screen. No, not possible, but probably I can just write that we will find that for this case, when we have a transition from Mach 1 to stagnation conditions, T0 divided by T would be equal to 1.2. 1.2. So we see that temperature on the wall, stagnation temperature on the wall is at most 20% higher than temperature after the shock wave. So we can have this rise of temperature. And if I take square root from this value, I can see how much is different speed of sound. So I take square root of 1.2 and see it's 1.1 more, approximately 1.1. So A divided, or A0 divided by A is 1, approximately 1.1. It's a bit smaller than 1.1, but I can do such kind of rounding. We see that change of speed of sound from stagnation point to point close to shock wave is at most 10%. Not so much, but we have this difference, this change of speed of sound. It means that is not constant velocity of propagation of these disturbances in our system. It cannot be considered as constant because 10% is already a considerably high value for such kind of calculation. So accumulated disturbances at one specific position on in space create this position of bow shock wave. So bow shock wave or any kind of shock wave is an accumulated disturbance of pressure waves of pressure waves. In this point of shock wave, we have a balance between energy that comes from infinite conditions, high velocity energy, and low velocity energy that is mostly generated by pressure distribution. So pressure gradient acts against the flow and creates such a barrier, accumulated pressure waves that form shock wave. That Anderson reminds and extends this idea in case of oblique shock waves, showing that in case of moving body or body with change in geometry, we have such a conical shape of wave structure, right? We have for subsonic case distribution of or the propagation of disturbances going in all directions, because in this case velocity of disturbance propagation is higher than flow velocity, and in this case summating velocity of movement and probably subtracting velocity of movement minus speed of sound, we have movement that can go against the flow. In case of supersonic velocity, this subtraction will always be positive. So flow disturbances can go only in direction of the flow and cannot go in the direction of the flow. And also Anderson introduces a relation between velocity and speed of sound that is called Mach angle. Here we denote Mach angle as mu, and geometrically it can be calculated when we analyze a relation between speed of sound and velocity of movement. And this Mach angle, which shows us angle at which disturbances propagate, mu, geometrically can be calculated, as you may see, as a function of Mach number. We cancel time from numerator and denominator inside the equation, and we have just ratio between speed of sound and velocity, which is a value reverse proportional to Mach number. So propagation of any disturbance in supersonic flow is described by Mach angle, and this Mach angle is a function of Mach number. This is why actually it's called Mach angle, because it can be calculated when we know the value of Mach number. Mach angle by itself is an arc sine of 1 divided by m, as you may see from this relation on the bottom of your screen. When we know this Mach angle, we can operate with several parameters in the flow, and it will be very useful in our further discussion. Here Anderson shows the structure of chapter 9. Is talking about more about oblique shockwave relations, supersonic flow over wedges and cones, difference between such flows we will discuss, shock interactions and reflections, where we have several shock waves meeting at the same point. I will show you how to calculate properties of the flow on shockwave interaction. It's a very interesting question, and is not linear and cannot be calculated in a fast way, but it's not so difficult, so can be revised analytically how two or several shockwaves would interact between themselves. And it's very important application when we design aerospace structure that has several shockwaves intersecting with each other. Then we talk about the attached shockwaves which are not connected to the body, but shockwaves which are produced by flow and body in some distance, shockwaves that appear in some distance, like bow shockwave, for example. How to determine when this shockwave will exist, when it will be attached. We will talk here. And after we talk about Prandtl-Meyer expansion waves, flow model that allows us to calculate using disturbance model the flow properties. It's very different model that we saw until now, so it's quite interesting for my opinion. First of all, we talk about model or development of the model in case of oblique shockwave. If you remember, in case of normal shockwave, we had rectangular control volume. And here, since flow is not parallel to the flow, we have such a control volume, which we might see on the screen. Here, it consists of two parts. It has edges A, B, and F before the shock wave, and edge C, D, E after the shock wave. What is the geometry? Which is the geometry of this shock wave? Of this control volume. Control volume has two edges parallel to the shock wave. Okay. Edge A is parallel to the shock wave, and edge F and B, they are parallel to the flow. It is made because in such a case we can significantly simplify our flow model. For example, we will never have integral of flow of any quantity of mass, energy, or momentum through edges F and B. So for us, edge F and B will not produce any source or sink of mass, energy, or moment. By the same way is organized control volume for such a model after the shock wave. Okay, it has one edge exactly on the shock wave. It's same edge as first part of control volume, and it has an opposite edge D. This edge D is also parallel to the shock wave. Okay, so edges A and D, they have same size and they are parallel. And there are also two edges, edge E, edge C, which are parallel to the flow after the shock wave. So as you might see, flow does not cross edge E and C, and we will never see any contribution. Doesn't want to amplify anymore. We cannot see any contribution of to the flow through these edges. Okay, we will see in our calculation. Oh, sorry, I have some kind of noise. We have we'll just see flow through edge A and edge D. Yeah, and of course, transition between one part of the volume and second part of the volume, transition through the shock wave. If we write in a such way, or if we define in a such way our control volume, then continuity equation can have its form same as we had for normal shock wave. If we take a look on it, we will see that integral of mass consists only of two parts, through edge A and through edge D. Here, area of flow is same. As I told you, A and D have same size. And we have density that enters control volume and velocity which enters control volume, and density and velocity which exit from control volume. Simplifying this equation, we receive equation of mass conservation in case of oblique shock wave in such simple form that is absolutely same as we had for normal shockwave model. Okay, so density 1, velocity 1 product is equal to density 2, velocity 2 product, which is relative mass of the flow, enters and exits is same. Here we must also say one important aspect, that velocity 1 and velocity 2 are not total values of flow conditions, right? We see that according to the vector of velocity, m which enters, or m infinite which enters in our system, it has to be split into perpendicular vectors. So we must split velocity in direction which is perpendicular to our shock wave. It is denoted as u1, velocity, perpendicular component, and mn1, it's Mach number normal to our shock wave. And we have also parallel component to shock wave, which is W2. It must be not W2, okay, it must be W1 probably. W1, and it's, as we will see analyzing momentum equation, W1 is equal to W2. So this is why W2 is present on the schematic, not W1. W is a second component of velocity, okay? So we have U and W components of the velocity, not U and V as usual, but it's just a question of name. And MT1 is Mach number tangential to the shock wave. We can split this vector of M1 when we know angle beta. Angle beta is angle of the shock wave, inclination between direction horizontal, in such case direction of velocity before the shock wave. We know that this direction of M1 is same as horizontal direction. So this is why beta is calculated in such way as shown. But usually we have to say that beta is this, when I write again this M1 here. So beta is velocity, oh no, sorry, angle between velocity before the shock wave and inclination of the shock wave. So it's not always horizontal. So you cannot use horizontal line as a reference. We use as a reference always parameters that we had before change of the flow happened. In such case, direction of the flow before the shock wave. If we have, for example, originally inclinated Mach number M1 like this, so beta will be calculated according to this relation. So, for example, shock wave is going like this, and beta would be defined in a such way. It has always a reference to Mach number before shock wave. Do not forget this very important observation, because in many cases we have to change direction of the flow, and if we have, for example, 3 shock wave, as in case of work 1, we always change the reference to beta. I will show you this in a few examples. I hope it will be much clearer when I explain you inside calculation. Okay. So we split this Mach number, and I think it's not so difficult to do. We probably can write somewhere on the side that U, or no, but maybe not U1, or Mn1 is, since it's a normal component of the velocity, can be calculated as M1 multiplied by sine of beta. Okay. Bigger is beta, bigger is M1. M1. M and 1. Please let me know if I'm correct, if there is some mistake or not, because I do not see a book right now. I cannot check. But we have this in next slides. We have something similar to this. Just let me see. Yeah, M and 1 is this equation. So it makes part of our model. So this is why we pay so much attention on splitting of our initial Mach number. We have a question: how is beta related to mu? It's not simple relation. We will talk about it in very soon today. Very soon we will talk about it. Of course, beta has a relation to mu because it's a formation of the oblique shock wave through limiting Mach number, limiting Mach angle. If we return to figure 9.5, we can see that oblique shock wave angle beta is always bigger than mu. Okay, so we have some kind of a lower limit where oblique shock wave can stay. We can see as a qualitative characteristic that beta received by calculation is always bigger than mu. But how much bigger we will see very soon when we elaborate equation for beta, equation for this quantity. So let's go back to this picture. Just more few comments about this discussion. We also have to split our Mach number, which we receive after oblique shock wave M2. It also will be split in the same way as we had for Mach number before shock wave. We have one normal component, Mn2, that is Mach number normal to oblique shock wave, and we have Mt2, okay, Mach number which is tangential to our shock wave. Here, to split this system or this vector into system of vectors, to perpendicular vectors, we also have to use so-called theta. Theta is the angle which is built between Mach number before shock wave. Also, M1 serves for us as a reference. Do not forget M1 as a reference, and Mach number after the shock wave. So between these two Mach numbers, between these two vectors of the flow, we have our angle theta. We are lucky in case of oblique shock wave that theta is always known. Theta is always known. Just a moment, I will see if I can show you from here. Probably not, but okay. We did not put here the source of oblique shock wave. As you know, source of any kind of shock wave is interaction between flow and body. So body is not present yet. I will try to put in another color. Yeah, okay, this is the body wall here that generates our oblique shock wave somewhere here, and it touches, the shock wave touches the body. What is good in all this story that this inclination of flow after the shock wave is always corresponding to geometry. So geometry body theta, which is defined as angle between previous Mach number before shock wave and direction of the body after the shock wave, is the same as theta for velocity change. So this theta on diagram of vectors is same as theta geometrical diagram. So to define theta, we need to know flow direction before shock wave, and we need to know direction of the wall after the shock wave. In such way, we can define theta angle, physical angle of the body. So when we define geometry, we always know how big would be this theta. Once we define theta, we can find a relation between normal component of Mach number after shock wave and total Mach number after shock wave. I can see from here that this is theta, and we also had beta. So where is beta in this all this story? Just a moment, I will remove body, not to have too many drawings here. And we see that also this, I will extend this angle here is beta. This one here, this small angle here is a difference. Beta is bigger and theta is smaller, so we make a difference of angles beta minus theta. And according to this definition, we can write that M2 is Mn2 divided by sine of this difference, beta minus theta. So in such way, we can see how big would be our angle, or not the angle, sorry, how big would be our Mach number after the shock wave. For this, we need to understand the values of angles, and we need to understand value of Mn2. How will be this transition of the flow, and how big would be Mn2? This we will do in a very, very few steps. On the next slide, we can see application of, sorry, there's some, can I remove this stuff? There is application of momentum equation to this control volume. As we might see, since we have two components of the velocity, u and w component of the velocity, we have to deal with two momentum equations. In case of u component of the velocity is this equation here, integral open. And in case of w component of the velocity is the second equation here, which is extremely simplified. Oh, no. No. Let me see. Oh, no, this is the w component of the velocity only. Sorry. It's just simplify the first one. The first equation is simplified because from continuity equation, we already have this quantity equal to this quantity. So these two products, they are same, so they can be canceled from our equation. And we find that we have conservation of w component of the velocity before and after the oblique shock wave. So W1 is equal to W2. This W1 is again right here. I show this image as it is in the Anderson book. So keep in mind that there is such kind of misprint. And even on the fifth edition, I do not remember how is it on the 6th edition, but on the 5th edition still remains this problem. We can also check 6th edition. But it should be W1 because we split our velocity before shock wave. And according to this momentum equation, we see that W1 is identical to W2 on its value and direction. And it's not a problem to write W2 here also on this part, on the left part of our schematic. So as a consequence, applying momentum equation to our system, we see that tangent component of the velocity is remaining same after oblique shock wave. What happens with the normal component of the velocity? This equation is shown here. Yeah, now it's normal component of the velocity. We see it's absolutely in the same form as we had for normal shock wave. We have a part of flow of momentum through the edge, right, due to the velocity and density. And we have our pressure forces that act normally on our control volume. And it's written right here. After we can simplify because we know that area is same. So area A1 and A2 are cancelled from this equation, and it can be rearranged in a such way that all parameters that are before shock wave, they are on the left side of momentum equation, and parameters on the right part are after the oblique shock wave. As you may find, this equation is absolutely same as we had for normal shock wave relation. This equation does not involve any quantities that describe position of shock wave or inclination of this shock wave. You can see that inside momentum equation, we have just flow quantities that enter and nothing related to direction of or position of this shock wave. Then we apply energy equation to this discussion. We see that energy equation can be written in the same form as we had for normal shock wave theory. In integral form, of course, it's stationary equation without any kind of time derivative. Then each of these integrals is open. On the left side of the equation, we can see flow of energy through the surface of control volume. We consider only surface A and surface D, because through other surfaces, we do not have any kind of flow. And on the right side of this equation, we see flow of energy created by pressure force. Yeah, okay. Repeats absolutely same equation that we had for normal shock wave. Velocity V1, this big velocity vector, is simplified because W component of the velocity before and after shock wave is same. So velocity V can be just substituted by velocity U because W component is same, so it's cancelled from our discussion. We can see that as a result, we have stagnation enthalpy definition on the left and on the right side, H0 right on the left side, and the stagnation enthalpy on the right side of the equation of the shock wave, and it's equal. We see that stagnation enthalpy and as a consequence stagnation temperature does not change through the transition in this transition through the shock wave. Now we can summarize everything that we already saw in previous equations. We see that there are totally 4 equations. 3 first equations are absolutely same as we had in theory of normal shock wave. And there is fourth equation which is different, yet belongs to just oblique shock wave theory. For us, it's a very big advantage because we already know how to solve flow properties that change through normal shock wave. So we take this model, we make calculation of normal component of velocity before shock wave, and calculate in the same way such transition from U1 to U2 according to normal shock wave theory, because all equations are same. And after, we just need to split, join back these vectors of tangential velocity component before and after the oblique shock wave. So 3 steps. Step 1, split velocity before shock wave. Step 2, use normal shock wave. Oh, this is step 1. This is step 2, use normal shock wave theory to calculate transition through oblique shock wave. And step 3 is join back vectors after the oblique shock wave. So 3-step calculation. Very simple case. If we write this in terms of our thermodynamic properties, because we already had model for oblique shock wave, this first step, step 1, when we split our system, is written here in a very simple way. We just need to know angle of the shock wave, and we can perform such calculation because Mach number is a value which is given before calculation. We know it's our initial value for calculation. Then step 2, we use calculation through normal shock wave. We obtain Mn2 normal component of Mach number after shock wave. And then we have step 3, where we use this normal component as input data, and we calculate Mach number after oblique shock wave. 3-step. Split, calculate by normal shock wave, and join back vector of velocity. Now, very interesting question. How to calculate angle of the shock wave? How is beta related to mu, right? As you can see here, as a final answer, beta is not a function of Mach angle, but it has a relation to Mach angle in some way. So how a model of beta can be elaborated? For this, we use 3 equations as entrance. First is that geometrically, angle beta can be calculated as ratio, or tangent of beta can be calculated as ratio between velocities, simply as ratio of normal component of the velocity and tangential component of the velocity. Again, here I remind you that W1 is right here. Okay, I intentionally did not change anything on my slide before because you need to know that in the book it's written different. So this is equation 1, geometrical definition of beta. Second equation is geometrical definition of difference beta minus theta after shock wave. Is simply ratio between velocities, normal and tangential after shock wave. Okay, as I already wrote you before. But now we see it's in a tangent, right? Not in sine. And the third equation is relation between velocity before and after shock wave. It's purely continuity equation. It's a continuity equation which says that mass before shock wave is same as mass after shock wave. These 3 equations, they have an intention to find a relation, not to solve it analytically, right? But just to write the system as one equation, put all together, and also we have to make transition from velocity to Mach number. This is done by known relations, that velocity is always related to Mach numbers through speed of sound. Speed of sound, probably. And combining these three equations, we obtain equation. We can see this big one, which can be simplified, and we obtain equation 923, which shows us relation between theta, angle of the body. This angle of the body, again, I will write you here. No, the angle of the body, or angle of inclination of Mach number after shockwave. But I prefer to use angle of the body because it's constant, right? I mean, body does not change. Body does not change on our calculation. So theta is angle of the body, beta is angle of the shockwave, and m is Mach number, the Mach number before the shockwave, m1 as input data. This equation has three unknowns, so it cannot be solved in a way that analytical, right? As a relation, how big is beta angle? In general, we cannot say because it's a function of two unknown parameters, but in a practical way, it always can be solved. First of all, because theta is known, so we know how big is angle of the body, right? Because we work with some known geometry. So we know theta, we know right part of this equation. And in most cases, we also know Mach number before shockwave. For example, m infinite, that happens on a far distance from the body. We start calculating from m infinite, and we know this Mach number. So we have only one unknown in this equation, which is beta, and it can be solved, unfortunately, not analytically, but it can be solved in some numerical way. You see here, generally, function beta is complex. There are some solutions on this equation. In particular cases, you can find in the literature also such solutions, but in general, I'm not recommending to find this kind of analytical solution, because numerically, for example, by method of Newton, we always can find an appropriate value of beta in a very short text on MATLAB, for example. In a practical way, this theta beta m relation, this is called theta beta m relation, equation 923, can be solved only in class graphically. Anderson shows this diagram in the book, and it corresponds to figure 9.9 from the book, that shows relation between angle of body is this lower axis is theta, angle of the body. Here we have beta, angle of shock wave, and these lines are different values of Mach number. I will try to zoom again. I don't know why I cannot make zoom of this. Just a moment. I will try to. I cannot change scale. Maybe I fixed somewhere this scale where I do not see where to. Where can I change this scale here? Before I could, but now not. For next class, for sure, I will be capable to change it. But I hope that you can see the numbers on this diagram, even though if they are very small. I hope you can see these numbers that, for example, theta angle is changing from 0 to more or less 58. at most, and beta is changing from 0 to 90 degrees. Here also 0 and 90 degrees on the top. Please let me know if you can see these values, so I will continue, or if I needed to find a way to make zoom. Are these values visible on this plot? Okay, thank you, Mauricio. Thank you. So these values are visible, so I can continue. This is a graphical representation of formula I just showed you, 923. So we use O formula, or we use this graphical representation just to solve something fast in the class. Is similar to appendix A, B, and others, but we cannot put this diagram inside appendix because it has two parameters. It has Mach number and angle, so it's not possible to create a simple or small table to be used. It's much better to make it in a graphical form. How to use this table? We can see that Mach number changes. The value of Mach number may be seen on this part here. I will draw a few of these values just for you to track. These red circles which I draw, they show different Mach numbers. We see it starts from Mach 1 on the left side of graphics and then increases to Mach 2 is over here, Mach 2, okay, is right here. And then it increases to high supersonic values, and here at the almost at the end we have Mach 5. Okay, this is Mach 5, and then it goes to supersonic to infinite, actually, to infinite Mach number. So this function has a limit. When we draw until infinite Mach number before shock wave, we see that angles of shock wave, they do not change anymore. Even though if we have hypersonic flow or very, very high velocity flow, angle of shock wave stops to change. It continues to be same. Okay, so here we have Mach numbers, and these lines correspond to Mach numbers. Just a moment, I will draw you. For example, for Mach 2 line is this one. Okay, this is the line for Mach 2, approximately. How to use such information? How to define properties of shockwave inclination? Very simple. For example, I have a physical body. I will draw it here on the side. This physical body is 20 degrees. 20 is good. Yeah, more or less 20. I don't like 20 because it's already close to a limit. Very high value of flow inclination. So there is an oblique shock wave like this. Definitely shock wave angle must be bigger than 20 degrees not to stay inside body. So shock wave cannot stay inside the body. This is why beta is always bigger than theta. This is very important when you implement equation for theta beta m analytical inside your work. You need to check this relation. Beta you obtain must always be bigger than theta you set as a body angle. Please pay attention on this in future, so your shock wave will be viable. Will not stay at least inside the body. So I have, for example, angle 20. I found where is my 20 of theta here below. I made a blue circle, and then I go up and I see where it intersects with my Mach 2, right here at this point. Okay, And after I go left, okay, and I see the angle. So here is this angle. It will be, I will make some approximation, right? Approximate value 53. I think it looks like 53 degrees. 53 degrees. So my angle of shock wave is 53 degrees. Same thing we can do in this direction or in any other direction. For example, I need to create a shock wave of some known value. And okay, my shock wave should be, for example, 40 degrees. If I need a shock wave of 40 degrees and I know that I have Mach 2 inside my flow, I will just go left. I will see where is the intersection of this angle with my Mach 2, and I will go down and I will see which body angle I should have. It looks like that close to 11 degrees. Close to 11 degrees. So if I have a body of 11 degrees and I have Mach 2, nice question, Luis. Just a moment, I will explain. And we have Mach 2 that we will have such geometry of the flow, exactly 40 degrees. Luis is asking why not take second intersection. Second intersection, it means that if we extend upper this curve analytically, right, we can find another intersection. Okay, in case of 20 degrees of the body, we will find that there is another point that has intersection with the diagram. Also exists analytically, such a thing, but it does not exist in the physical world. It's a so-called imaginary solution. We never will find such a flow in a real life. Anderson also explains this from point of view of computation calculation. He says that there are two different types of shock waves. Just a moment, probably is here on this diagram. It's same diagram, but more clear, because first one I showed, this diagram I showed from the book, and the second diagram I just found on other reference. It's very simple. You can also build such a diagram by yourself in MATLAB, for example, or any other software. You just plot this function, you will find it. So he shows that there are two solutions. This so-called weak shock solution that we are looking for is called weak shock. And there is another strong shock that we are not looking for such solution because it does not happen. But this equation has two roots. Because if we analyze this equation, it has a Mach in square. So definitely there's a parabolic function. And this parabolic function has two roots usually. Any parabola has two roots. So this is this case. Strong shock we are not looking for. We are just analyzing a weak shock solution. Okay, this is why not second intersection. Strong shock is something that is close to the attached shock wave. In case of the attached shock wave can be used some part of this information, but is not so much practical for oblique shock wave calculation. A lot of discussion can be seen. Mathematical analysis in this case very useful. As for practical application, I tell you, need to use just forced solution. And also, please pay attention on the following, that this relation between theta and beta, right? That beta is always bigger than theta. And another I will comment to you. Just a moment. I have another question. M2 should be less than 1. So if the upper intersection isn't the correct one, no. M2 is not more than 1. If we go back to the theory of, let me go to one of the schematics we had. M1 is supersonic, okay, is always supersonic. And according to oblique shockwave theory, M2 is also supersonic. Flow remains to be supersonic. This is another checkpoint in your calculation. If you receive M2 as some value smaller than 1 is wrong. You need to find an error. Okay, so oblique shockwave theory says, and not just theory, but also real life says that flow remains to be supersonic after oblique shockwave, which is completely different from normal shockwave. In the normal shockwave, flow is supersonic before shockwave and flow is subsonic after shockwave. Okay, so pay attention on this. Jan, I hope I answered your question. Please let me know if you can you not force strong shockwave occur? I did not understand this this question. Difference between strong shockwave and weak shockwave is, I think, more theoretical than practical, and anyway can be studied by the book. In our applications, we use just weak shockwave. We never use strong shockwave. If we cannot force strong shockwave to occur, we never force strong shockwave to occur. We always have a weak shockwave, or we have the attached shockwave that we will study soon. Another, please let me know if you have another question, because I would like to understand better, sometimes better, your questions. That simple question is difficult to answer, right? It's usually like this. Pay attention on another thing, that each oblique shockwave has its limit. For example, if we look Mach 2 on this diagram, we see that there is an extreme point here, an extreme point, theta is equal to theta max, okay, an extreme point that says us which could be the angle of the body, that maximum possible angle of the body that caused this shockwave. It means that if we work with the angle of the body on this direction after, and Mach 2 will never receive solution, we will never receive intersection of Mach curve with the angle. It means that oblique shockwave will never happen. What will happen in this case will happen the attached bow shockwave or normal shockwave. So each geometry, or let's say differently, oblique shockwave should be compatible with geometry and Mach number. Geometry limitation is from 0 to this maximum theta angle, okay, and Mach number limitation, according to this diagram, also saying to us, I think I did wrong. This is Mach 225, not Mach 2, 225. Saying that Mach number also limits the geometry. For example, we work with Mach 1.4. It means that we can have maximum 9 degrees of the body to obtain oblique shockwave. It's better to work at smaller values, so we will have this intersection, right? If we already have, for example, 15 degrees and we have Mach 1.4, intersection will not happen. So in this region, we will definitely know that it's a normal shockwave happening. When you calculate by your models, please also pay attention on this on this aspect. So you need to have not just Mach number and solution compatible, right, but also geometry compatible to have intersection and to have a solution of flow equation. Once we are talking about this question of model, we see here on this screen a complete set of equations you need to have to calculate one oblique shock wave or a series of oblique shock waves. So ER equation on theta beta m relation between flow inclination and oblique shock wave angle, and Mach number before this shock wave. These three quantities, and again, I repeat you, split velocity in two directions, calculate just normal component of the velocity by normal shock wave theory, and unite velocity at the end and receive the final Mach number. This is what happens when we are inside or outside limit on theta. Anderson explains with pictures. When we did not reach yet the limit of theta max, maximum possible angle of the body, we receive attached shock wave, and this shock wave is oblique. And if we exceed our angle of the body, flow becomes detached, right? And it usually has bow configuration. Oh, but I think it mostly depends on how we interpret and this geometry shape. It can be different shape. We cannot say that it's a spherical shock wave, for example, or it's more, how to say, oval. It all depending on the geometry. There is no analytical model or no analytical calculation that says us which is the shape of this shock or bow shock wave or the attached shock wave. Shape cannot be found analytically. At least I never saw such a model. No, it's not true. One time I saw a model that describes shape of bow shock wave, but unfortunately this model was so complicated, so big, it had several pages of equations that we could not use it. So this is why I never saw working model for the attached shock wave. But there is one report of NASA that says about geometry of a bow shock wave. Unfortunately, we could not implement because trying to calculate all the set of huge equation system, something was wrong. Something did not work, and probably some or misprint or some wrong boundary conditions, because it's a set of differential equations, not ordinary differential equations, but a set of a big number of equations, and we could not, unfortunately, make it work. Tried several people, but I think there is an error in or mistake inside the publication, intentional or not intentional mistake. But okay, it's not a question. I tell you that the attached shock wave cannot be solved analytically. At least I could not solve it, and can be solved in a much more simpler way numerically when you simulate flow inside Fluent, for example, or other software, or if you do experiment, also you can observe this bow shock wave geometry experimentally. For my opinion, numerical simulation is much simpler nowadays than experiment. So I recommend you, if you would like to do such kind of calculation, it would be very nice practice. Anyhow, I almost sure that everyone will have the attached shock wave on a simulation of work 2. It's almost inevitable once you did not optimize numerically geometry for such simulation. So the attached shock wave is a very common problem appearing on simulation of diffuser when especially subsonic part of this diffuser is not optimized yet. I also showed this in some of the videos, and I will repeat about this for people who will be interested, who will be having same problem of simulation. We will discuss how to solve such a problem. But I have several videos just about the attached shockwave and problems of not receiving or simulation when we have this shockwave and we do not want to have the attached shockwave. It's not good, absolutely not good from point of view of performance and flow properties, and we have so many losses that aerodynamic structure cannot fly efficiently if it has big detached shockwave. This shockwave appears. It regularly appears, for example, for re-entry bodies. But if you would like to fly it and accelerate, the attached shockwave kills all the performance. More details about this question we can discuss in case someone will have interest to talk. I don't think we have so much time in our regular conversation. But if someone would like to know more about this, I'm ready to talk. Then also on the lower part of this slide, you can see similar figure, which is corner flow. Corner flow has absolutely same characteristic as the wedge flow. Wedge is symmetric, right? Corner is just one side. Since we do not see any boundary layer, we do not involve theory of boundary layer, let's see, in such calculation, we can consider these two cases of wedge and corner as identical. And from computational point of view, we will never see difference. So wedge and corner, once they are both bidimensional, they have absolutely same flow and characteristics of theta max. They are same for both of such cases. Okay. I think we can leave a calculation of oblique shockwave for next class. Today will not be enough time to provide one calculation, but starting from next class, I will give you several examples of calculation complete. One oblique shockwave and several oblique shockwave in a sequence, so you will know how to construct your computation in work one. If you would like to start already, you can do it easily just looking previous videos where I show already such a calculation of oblique shockwave or series of shockwaves. Such video already exists in the list and you always can see it. If you can wait, on Thursday, I will explain one more time because I consider very important to show how, as much as possible, examples how one or series of oblique shockwaves can be calculated. On figure 9.12, Anderson shows dependence on Mach number. Theta beta M relation influence on, no, not, can be used for analysis of influence of Mach number. So we can see for same geometry, theta 20 degrees in both cases. When we change Mach number on infinity, how is different beta angle of the shock wave? In first case is bigger. When we increase Mach number, angle of shock wave becomes smaller from 53.3 to 29.9 degrees. Not just the beta, not just the angle of shock wave is changing, but also we have change of all properties, all thermodynamic properties and flow or Mach number properties after this shock wave occurs. So it's not just depending on beta. Since beta is inside this equation system, is a first step, right? We define beta, and then we provide all this calculation. We have impact on all flow properties. Once we change input, output, all parameters will be different. In slide 20, figure 913, we have dependence on angle of the wedge or deflection angle. Bigger is the angle, bigger is the angle of the body, bigger is the angle of the shock wave. Smaller is the angle of the body, smaller is the angle of the shock wave. And also, since it's initial or input values for our model, all other properties are changing. With the smaller value of the body angle, we have smaller Mach number, right, of normal Mach number, and we have also smaller pressure rise through the shock wave. Bigger angle of the body Mach number is also bigger, normal component, and bigger would be the range, the ratio between pressure. Okay, from this example here, we will start our next class. I will show you comparison between calculation of normal and oblique shock wave and the normal shock wave. And we will define from point of view of efficiency, which type is better. Already, we can revise that combination of several shock waves is always better than just one shock wave. More sophisticated flow structure and better performance. But this we will see numerically on Thursday. And then after this example, I will show you several other examples how to make it in a sequence in a very simple way. Please let me know if you have questions. Just a moment. You can write your questions. I will need to answer a call. So I see no questions for today. Okay, people, thank you very much for participation. On Thursday, we will continue this calculation, and I hope it will be more clear. Try to provide some calculations by your own, right? Try to build this model to see how calculation can be done, and it would be very useful, I think, to discuss this. What is the importance of Mach angle? We will see it. We will see it. Still in this chapter, it's used widely in expansion waves, because expansion waves is something that is related to propagation of disturbances, and Mach angle is a pure purely giving direction to angle of disturbances propagation. So expansion wave uses this concept of Mach angle. We will see it when we discuss expansion waves. Please remind me if will be not clear how is integrated theory of Mach angle to expansion waves. I will pay more attention on this question, okay? So I see no more questions for today. Thank you very much for participation today, and we meet next time after tomorrow. And have a nice afternoon. Have a nice evening. Goodbye, everyone.